Welcome to qnawire.
I'm going to explain briefly the following methods of electronic structure. So we're going to begin with MP2, which is going to stand for Molar-Placet perturbation theory. At the second order. So what is going to occur is that in general, whenever we're doing any perturbation theory, what we're going to get is that our Hamiltonian, we're going to write it down as a portion that is going to be exactly solvable plus lambda times the perturbation. And in theory, this perturbation is going to be small. In the case of Molar-Placet perturbation theory, the initial wave function at the zero order is going to be an eigenfunction of the Fock operator. Thus, the general wave function for any Molar-Placet up to any order is going to be the expansion from 0 to m, where m is going to be the order of the perturbation, of lambda I, which is going to be the parameter elevated to the power of I times the wave function associated to that section. So in the case for MP2, what we're going to get is that the wave function at MP2 would be equal to phi 0 plus lambda phi of first order plus lambda squared times phi of second order. So what is going to occur is that the equations that are going to give us the energy for MP2 are going to come from the introduction of these ansatz into the time-independent Schrödinger equation. Over here, what is going to occur is that our Hamiltonian is going to be h0 plus lambda times the perturbation times our wave function. That is going to give us the sum over I equals 0 of lambda I times the energy up to the order of perturbation times my wave function. So over here, equating all of the terms all the way to order lambda k is going to give us MP of k order. So we're going to only equate terms up to k equal to 2 in second order perturbation theory. In particular for MP2, we're going to see that first of all, the energy of MP1 is going to be equal to 0. This is going to be directly the wave function times the perturbation times the initial wave function that we're going to use, and this is going to be a consequence of Brillouin theorem, which tells us that first order excitations, meaning that singly excited as later determinants, will not contribute to energy corrections. And the energy at MP2 would be equal to MP, let me write it down over here, MP2 would be equal to an expression which involves 2 times the sums over I, J, A, B, AB potential Ij over the orbital energies minus epsilon A minus epsilon B minus a term that is going to correspond to the exchange. So the exchange term is going to be, let me write it down. We're going to get this value for the energy, where the second term is going to be the exchange. And in this case, this is going to be the particular formulation for a closed shell. Remember that rhos are going to be canonical orbitals. and index I and J are going to correspond to occupied, and A and B are going to correspond to virtual orbitals. Okay, so that would be for MP2. So of course this is going to be a very brief explanation of this method, and I'm going to do the same with the other three that we have at hand. So next up we're going to have couple cluster singles and doubles. In this case, for couple cluster, the ansatz of the wave function is what is going to change. So we're going to have that the ansatz is going to be an exponential of an operator, that is going to be our couple cluster exponential operator times our wave function. In most of the cases, this initial wave function is going to be equal to the Hartree-Fock reference that we're going to employ. So on the couple cluster singles and doubles method, what is going to occur is that the operator T is going to be equal to T1 plus T2, meaning that we're going to include only single and double excitations from the cluster reference. So the T1 operator is going to be equal to the sum over I, sum over A, where both of them are going to be occupied, and these are going to be virtual orbitals, of a certain amplitudes that we're going to solve in the couple cluster method, times the excitation operator corresponding to this. So depending on the case that you're dealing with, sometimes this is going to be the notation. This is going to be alternatively be seen as A dagger A, AI. So depending on the notation that you're employing, you're going to have different expressions, right? So most of the chemistry textbooks are going to employ this second notation for the cluster operation. So following that convention, the value for T2 would be equal to 1 over 4, sum over I and J, sum over A and B, of Tij AB, of A dagger A dagger B, A, J, AI. And all of these are going to be creation and annihilation operators on second quantization. So this is going to be the essence of the couple cluster method. Then you are going to apply the couple cluster equations, which are going to give you the energy. In particular, this wave function, which is the couple cluster wave function, is going to be applied in order to get, in which what we're going to do is going to project the set of the excited determinants into a solution. So what we're going to get initially is going to be that our wave function on the couple cluster method applied to the Hamiltonian times the wave function of the couple cluster method is going to give us directly the energy. But whenever we're going to have an excited configuration, what needs to occur is that and excited, I'm going to call this phi with asterisk, wave function in which we're going to apply the cluster operator needs to be equal to 0, where this one is going to be a singly excited determinant. And you're going to do the same thing with the other excited configuration. So for example, a double excited scenario is going to yield the same result, needs to be equal to 0 in the case of couple cluster singles and doubles. And the solution of these equations is going to give you the set of parameters Tijab and Tia that we got over here. So those solutions are going to give us the energy. Recall that these guys are going to be called cluster amplitudes. And finally, the easiest of the methods, and in this case, what we can do to extend to CISD and full CI. CI singles and doubles is going to include only single and double excitations. And full CI is going to include all possible excitations. So this is going to be the exact solution, since it includes all possible configuration state functions for our system. So what is going to occur on the CI singles and doubles is going to be that the wave function for CISD is going to be given by a certain coefficient times our starting Slater determinant plus the sum of the single excitations that were going to come with the associated coefficient. In this case, we're going to label this wave function as 8R, plus the sum of C, our S, AB, which is going to be phi AB RS. So these are going to be singly excited as later determinants, and these are going to be doubly excited. In general, the configuration interaction method is going to lead to a matrix eigenvalue equation in which we're going to have the following: HC is going to be equal to an eigenvalue matrix, which usually is going to be called the energies times the overlaps times the coefficients. So C are going to be coefficients, H is going to be the Hamiltonian matrix, which is going to be defined by the matrix elements phi I Hamiltonian phi j, which each of them are going to be combinations of different Slater determinants that we're going to have, and S is going to be the overlap matrix defined by phi I phi j. In the case of Slater determinants, Sij is going to give us delta ij if we're using Slater determinants. So over here, this is going to be the way that we're going to solve for the configuration interaction method, and the only difference in between CI singles and doubles and full CI is the number of excitations that we're going to include. So over here, the wave function for full CI is going to contain all excited configuration state functions, all the possible Slater determinants with n number of electrons. And with that, it would be all. This was the as brief as possible explanation of all of the methods. I'm sorry if I didn't go into enough detail on one of the subjects, but this is going to be the general idea. So MP2 is going to be a perturbative method. The wave function is going to be corrected at first and second order, and we're going to equate the terms of lambda according to the order of the perturbation theory, giving us expressions of the energies of MP2. For coupled cluster, what is going to occur is that we're going to have a coupled cluster operator associated to the excitation of single and double excitations times an exponential. Sorry, I think that over here was e to the minus t. Sorry about that. And what we're going to do is to project the coupled cluster wave function onto the Hamiltonian to get energies and onto excited states, and either singly excited states and doubly excited states, in order to get the solutions for the cluster amplitudes, which are going to define our wave function at the end. And finally, for CI singles and doubles and full CI, what we're going to do is solve a general eigenvalue equation, the one over here on the right, based on the ansatz of the wave function. So for CI singles and doubles, we're going to include the reference Hartree-Fock Slater determinant and singly excited and doubly excited Slater determinants. And in the case of full CI, what we're going to do is include all of the possible excited configuration state functions, meaning all excited Slater determinants for that number of electrons. And with that, it would be all. Thank you very much, and have a good one.